Hello, today's lecture is about exact, or sometimes also called total differential. This is an important quantity when studying thermodynamics and also especially chemical thermodynamics. To know or to explain what the total differential or the exact differential actually is, we have to address a few prerequisites. Namely, first, I would like to state that we are given a function f of x, and y, and the partial derivatives of this function are continuous. At an arbitrary point or at a given point x naught, y naught. And f, x, and y are all elements of the real numbers in our explanation example. So if one is not familiar with the partial derivatives, this is quite easy. First, write down what actually this notation here means. It means that it is a partial derivative, and for example, let f of x and y be 3 times x times y. Then for the partial derivative with respect to x, we treat y as a constant. Therefore, partial derivative with respect to x equals 3 times y, and the partial derivative with respect to y equals 3 times x. So actually it's very easy. I will erase it now. I think one can remember it, just in case one has not heard about partial derivatives yet, to give a very brief explanation what it is. Next thing is, for explaining, let's draw a function, some arbitrary function f of x and y. For the purpose of explanation, let's make it look like a hat or a hill. So this would be our function f of x and y. And let's also draw the corresponding axis. So here would be, let's say, the x-axis. This direction we would have, let's say, the y-axis, and vertically goes the z-axis. So as the name already somehow suggests, differentials, we are interested in very small changes, or in a method of how to approximate very small changes in very small changes of f. So to do this, let's make first a comparison in the one-dimensional case. In the one-dimensional case, we have functions which depend only on x. So let this be here f of x. And what you also can do we can approximate the function f of x at the given point x naught with a tangent line. So close to x naught, the tangent is a good approximation of f of x. Let's call tangent here g of x. And the formula for g of x actually is, it is f evaluated at x naught plus the first derivative of f evaluated at x naught times x minus x naught. So we can do the same here for this two-dimensional function at some point x naught, y naught. So we can choose here the point x naught, y naught. So let's project down to the xy plane. So here would be x naught, and here would be y naught. And if we hold, or if we would like to make a tangent parallel to the x-axis, we can draw it like this. I'm not a very good drawer, actually. But this, let's say, tangent parallel to the x-axis can be described with the following relationship, because our partial derivative is continuous at the point x naught, y naught. So therefore we can write this line would be described by df over dx evaluated at x naught, y naught times x minus x naught plus f evaluated at x naught and y naught. So it's pretty much the same as here, only that we use partial derivatives. So the same we can do, because the partial derivative with of f with respect to y is continuous at this point here. We can also draw a second tangent line, which would be described by the equation df over dy evaluated at x naught, y naught times y minus y naught plus f evaluated at x naught and y naught. And these two functions, they define the tangent plane to the function f at x naught, y naught. And because the partial derivatives are continuous in this point, this tangent plane exists at this point. So it's the same as in the one-dimensional case, but instead of approximating the function with a line, we are approximating the function here with a plane. So now in the next step we can already move closer to what are we actually interested in, namely the exact differential. Therefore, and as already said, we are interested in changes of f. We define delta f as follows. It is f evaluated x naught plus delta x and y naught plus delta y minus f evaluated at x naught and y naught. And as you already saw in the one-dimensional case, this delta f is almost equal to changes in the tangent plane. Because let's say if I move here, let's say some distance delta x, some distance delta y, then I end at this point here. But the difference between the two functional values can also be approximated when moving here in the tangent plane and calculating the difference here. So therefore I can write that delta f is approximately df over dx evaluated at x naught y naught times x minus x naught plus df over dy evaluated at x naught y naught times y minus y naught. And now I can set this property here to be delta x, and this property here is, or this term in the brackets here is delta y. So as delta x and delta y go to 0, this approximation sign here becomes an equality, and the change of delta of f becomes infinitesimally small. This means that df equals df over dx. I do not write this x naught and y naught here now, because we said that df and dy are continuous at every point in the region where the function is defined. And this delta x becomes dx plus df over dy dy. And this is already what we were looking for, but we are not done yet. This is the exact differential. With the prerequisites that we have a function given f dependent on x and y, and the partial derivatives of x and with respect to x and y are continuous everywhere, and actually also that the definition space of the function is a simply connected one. But don't worry too much about this. So the interpretation of this here is now that we can describe small changes of f with its partial derivatives. So that is the message for now. Later on, now I move on to explaining actually why the total differential is actually useful in physical chemistry. But before I continue, let's also state the general case. So if f depends on, let's say, n variables, f dependent on x1 up to xn, then the total differential is actually the sum of such terms. I runs from 1 to n, then we have n partial derivatives and n times dxi.